It's nice to see everybody, even though it's in little rectangular form, that's fine. What I'll be discussing is some joint work with Tom Needham from Florida State, Clayton Shonkwiler from Colorado State, and Soledad Villar from Johns Hopkins University. This paper will hit the archive tonight, but if you can't wait until then, you can check out this bit.ly link, and that'll get you the PDF. So I'll start by defining an object that I think most of us are familiar with. I'm going to have a short fat matrix, call it big Z. The columns are Z1 through Zn. This is going to be a unit norm tight frame. It needs to satisfy a couple of properties. First, it satisfies this unit norm constraint. That's saying that all of the columns have unit norm, go figure. And then secondly, if I take my short fat matrix and multiply by its conjugate transpose, I'll get some constant multiple of the D by D identity matrix. I want you to think of this as an isotropic sample of the sphere. Okay, so this is a pretty object, and accordingly it finds applications in a few areas. I'll rattle those off right quick. Harmonic analysis. In fact, harmonic analysis is where the general theory of frames originated. Later on, it was realized that you could use frames for signal processing. And today, I typically think about problems in metric geometry where unit norm tight frames frequently emerge. These unit norm tight frames, they're elements of a useful set of matrices to think about. These are matrices for which every column has unit norm. So I'm using an S here. I want you to think of like the sphere. Every column is in the unit sphere. Every unit norm tight frame belongs to this set. We'll actually see that it's a special member of this set. In order to make that super clear, we'll define the frame potential. This is a function that receives a member of S and kicks out a real number. And the way it's defined is you give me that matrix. I'm going to take the corresponding gram matrix of the columns and then compute the Frobenius norm squared of this. So this is the sum of the squares of the inner products between the columns of Z. So the reason unit norm tight frames are interesting relative to the frame potential comes from the theorem of Welch back in the 70s. So Welch thought about a bunch of different bounds, and if you read the tea leaves, he secretly has this bound sitting inside of his paper. So Welch tells us that the frame potential is at least some fixed quantity determined by our parameters, D and N. And equality in this bound is achieved precisely when Z our matrix is a unit norm tight frame. Okay, so the frame potential received its name from Benedetto and Fickus. They were actually thinking about back in 2003, they were thinking about what happens when you locally minimize the frame potential. So intuitively, you should be thinking of like an analogy to like point charges on a sphere, and they're repelling each other according to a Coulomb potential. And the frame potential is doing some sort of analogous thing and trying to sort out exactly what's going on there. Before I tell you the punchline, I want you to be aware that there are some seriously hard problems in the neighborhood of what we're talking about here. So, for example, the Thomson problem. This is looking for the optimal arrangement of point charges so as to minimize this Coulomb potential. The Thomas problem is looking at the generalization of Coulomb potentials to Riesz potentials and sending P, I think, to infinity, looking for the optimal configuration of points in a sphere so as to maximize the minimum distance, so like an optimal spherical code. And then Smale posed the problem of sending P from that Riesz potential down to 0. All of these are open problems that people are interested in solving. The reason these problems are so hard is that there seems to be exponentially many local minimizers to these things. And this is something of a defect in the objective function and the potential you're trying to minimize. What the Benedetto-Fickus theorem says is that the frame potential does not share this defect. So not only are there not exponentially many spurious local minimizers, there's actually 0 spurious local minimizers. If you were to locally optimize the frame potential, you will end up at a local minimum. You might be worried about hitting a saddle point, but most of the time you won't, at least in practice. So in this talk, we're going to discuss 3 modern proofs of this theorem. The reason being that there's been a lot of work over the last 10 years to drill down theory for how to show that there are no spurious local minimizers in a given objective function. Local methods have been the workhorse for a lot of signal processing and machine learning. And accordingly, people have been trying to come up with theory to explain why stuff like neural nets happen to do a good job of finding global minimizers, despite not trying that hard. So I'm sitting at a place in history where I have the hindsight of the last 10 years of theory, understanding these local methods, and I'm going to throw that theory at this Benedetto-Fickus theorem from 2003. So I told you there would be 3 proofs. The first proof uses words like Lagrange and Werdinger. I want to point out that this proof of the 3 proofs, this one smells the most like the original proof. So if you're not familiar with the original proof, maybe you'd be interested in this section for independent reasons. So the approach. is the following. First, the set of UNTFs, unit norm tight frames, is a subset of the global minimizers. If you're a unit norm tight frame, then you necessarily minimize the frame potential by virtue of this proposition. So this is by Welch. Okay. Next, if you're a global min, you are necessarily a local min. This is by Calc 1. Let's call it obvious. If you're a local min, then you're necessarily what's called a second order critical point. This is to say that well, if you didn't have constraints, it would mean that your gradient is 0 and your Hessian is positive semi-definite. If you have equality constraints, then you have to do a Lagrange multiplier version of that. So we'll call this Lagrange. And then finally, if you're a second order critical point, it turns out that you're a unit norm tight frame. And this is the work to be done. Okay. So I'm not going to take a bunch of derivatives for the rest of my time here. Instead, I'm going to share with you some stuff that I learned while doing this project that I think you might find useful in your various projects. When you identify what the second order critical points are, you have to take a bunch of derivatives. And so you're faced with the following question. How am I supposed to differentiate? Like I have a matrix Z and it's being mapped to its frame potential. So the thing is that Z is a complex matrix and this is a real number. The theory of Lagrange multipliers is very much a real theory. So it suggests that what you should be doing is you should be taking the real and imaginary parts of your complex matrix and then differentiate this function in terms of those real and imaginary parts. This is not pleasant trying to do that. Instead, I'm going to show you the idea of Wardinger calculus. So the first time that I learned about the existence of Wardinger derivatives is from a paper on phase retrieval called Wardinger flow. And the main idea is that all of the derivative information that you need from this function is going to be nicely captured using this alternative calculus. I think it's most easily digested with an example. Let's say F receives a vector Z and kicks out the norm squared of Z, okay? I'm going to show you by example what the partial derivative is. This is a Wardinger derivative of the Zi bar, okay, of this function. So so you might think to yourself, okay, I got this complex thing, I'm taking a bar somehow, and there's some sort of, how does calculus interact with complex conjugation? What's going on here? So the amazing thing of Wardinger calculus is if you have a polynomial of ZJs and ZJ bars, then to take the partial derivative with respect to Zi bar, you're going to formally take a partial derivative as if everything is constant except for zi bar, including zi. You're treating formally zi as an independent variable. So I push this in by linearity. And then this partial derivative vanishes except when I and j are equal. So I'm left with zi. Okay. So there's if I were to stack all of these Werdinger derivatives together, I would get a vector that's partial z bar of f of z. This is just the vector of these numbers stacked together, namely z. Okay. So I just explained to you how you compute a Werdinger derivative. Now I'm going to show you why it's useful. So in general, if you're looking at a first order approximation to your function, a little bit of symbol manipulation reveals that you get this quantity. Okay, which is to say that this quantity should be thought of as the gradient of your function. Here I'm taking the real part of this inner product because I want to view this as a vector in a real vector space, like treating each copy of C as a copy of R2 and just taking dot product in those real spaces. So it's this identity that compels us to write the gradient of f as twice this Werdinger gradient. Okay. So this greatly simplifies calculations, you could imagine. I only have to do these formal partial derivatives. In order to get a second order critical point, I also need to think in terms of Hessians, and it turns out that there's a similar encoding of the Hessian information. But I won't belabor that point. Okay. Instead, I'm going to move on to the second proof. Okay. So we'll start with a lemma. And I'll have you know this lemma is extremely useful. So if you turned your brain off for the previous part, I want you to turn your brain back on right now. So suppose I have a function that's open. So what that means is x and y are topological spaces. Okay, there's a topology underneath. And when I take the image of any open set in X, it ends up being an open set in Y. I want F to be something, also Y is going to be a convex set by virtue of me asking for F to be a convex function. Okay, so you should think of Y as sitting inside of a topological vector space, and the image of Z is Y, and Y happens to be convex. Okay, and then F is a convex function on top of that. If I have these two functions at my disposal, then their composition has no spurious local minimizers. Okay, so we're all very comfortable with convexity. And that convexity has no spurious local minimizers. This is one of the reasons convex optimization is so useful. Well, it turns out that if you pre-compose a convex function with an open map, then you still enjoy this feature of no spurious local minima. So for example, let's take a function that takes two real variables and kicks out this nasty quantity. Okay, so I'll try to plot this. I'm going to have a minimizing set along the unit circle. And then it gets a little larger here in the middle. And then it also gets larger outside the unit circle. And it gets even larger after that. Let's go dark blue? I don't know. Okay, so I don't really know how to describe this function, but the point is that your local minima reside on this circle. And you could kind of imagine trying to do gradient descent from any point, and it would send you to that a member of that circle. Maybe you believe from this picture that H has no spurious local minimizers. So a way to demonstrate that is to factor the function. So the input space is R2, the output space is R. We're going to introduce an intermediate space, namely the positive real line, non-negative real line. So we're going to have an open map from R2 to this non-negative real line. This is just going to take the sum of the squares. This will be our function g. And this happens to be open. Now, I have to be clear, I suppose. When I say open, I'm thinking of this as a topological space with the subspace topology from the real line. So if I take an open interval from the real line and I intersect it with the non-negative real line, maybe I'll end up with a set like this. This is an open set in this space. And accordingly, this is an open map. You can convince yourself of that. I'll be composing this with another function that sends z, give myself some room, to z minus 1 squared. This will be f, and this is convex. Okay. So by virtue of the fact that H is the composition of f and g, we get to conclude that it has no spurious local minimizers. Okay. So what we're going to do is we're going to throw this idea at the frame potential. In particular, we're given a function and we want to show that it has no spurious local minimizers. So it suffices to factor the frame potential. It's going to be a composition of a convex function and an open map. And I'll tell you what the open map is. It's going to be what are known as eigensteps. So eigensteps are a thing that Matt Fickus and a slew of other people devised in order to better understand unit norm tight frames. It turns out that you can construct every possible unit norm tight frame using the theory of eigensteps. And they've since been used to demonstrate cool properties of the algebraic set of unit norm tight frames. For example, they're path connected, provided certain conditions satisfied. We're going to use eigensteps as our open map here. So in order to convey to you what eigensteps are, Introduce some notation here. So lambda of A is just going to be what I get when I sort the eigenvalues of A. And when I say sort, I mean like decreasing sort. Like I start with the big number and then I go down. So notation here, capital sigma of a matrix with column Z1 up to Zn. So this is going to be another matrix of the same shape. The first column is going to be the eigenvalues of the outer product of the first column with himself. Okay, so it's really going to be like the first entry is the norm squared of Z1, and the other entries are going to be 0, right? The next column, I take Z1, Z1 star plus Z2, Z2 star, and take the eigenvalues of that. And I keep doing that with all these partial sums of outer products. So what's going on here is if you were to apply this map to the matrices with unit norm columns, then it's actually going to map onto a very nice set. This is known as the Eigensteps Polytope. I suppose I should say sigma is the Eigensteps map, and the notation's just a little bit clever. You ever notice that sigma kind of looks like a capital E, but then it sounds like an S? Well, this notation combines those interpretations for eigensteps. So cool. So the Eigensteps polytope is it's a polytope, so it's the intersection of a bunch of half spaces. It's defined by some trace equalities and interlacing inequalities. I'm not going to go too much more into detail on that. I will say that the main result of this section is that the map, the Eigensteps map, is open. When I say that, I'm thinking like in the subspace topology. This Eigensteps polytope is sitting inside of a real vector space. The real vector space has a standard topology, and then I take the subspace topology for the polytope. Okay. So the reason this is interesting is if you take the last column of the Eigensteps matrix, what you're getting are the eigenvalues of the frame operator. Okay. So if you take, let's do this. So given a matrix, I'm going to multiply by it should be n, the last standard basis element, and then I'll take the norm squared of that. This is the sum of the squares of the eigenvalues of our frame operator. This is the frame potential of our thing. So what we have is I apply an open map to Z, and then I have this convex map on top of that. So you can generalize this to get that every convex function of the eigenvalues of this frame operator has no spurious local minimizers. Okay. So, yeah, so it's a stronger version of the original. Okay, so on to the third part. Maybe I should pause for questions if there are any.
I guess not. And our audience has the opportunity to unmute themselves, so people can ask questions when.
All right, feel free to interrupt me. I feel like I'm talking a mile a minute here.
Could you possibly elaborate on why the eigensteps can be thought of as an intersection of hyperplanes?
Yeah, so this is not terribly trivial. I'll tell you why they're definitely contained in the polytope, but I won't explain why it's onto the polytope. So the reason it's contained in, there's a few, here, let me erase this and start talking about, right? So there's this notion of interlacing. So we say that X interlaces Y if the first entry of X is bigger than the first entry of Y, bigger than the second entry of X, bigger than the second entry of Y, all the way down to the last entry of X, last entry of Y, and that has to be bigger than, nope, I'll just leave it at that. Okay, so it turns out that if you have like a positive semi-definite matrix, call it A, and you look at what the rank 1 update of this looks like, it's going to interlace on the original. This is coming from Cauchy interlacing.
Yeah.
Okay. So those are all of the inequalities in this Eigensteps polytope. The equalities are coming from the following. So if I were to take the sum of the entries of, let's do j equals 1 up to, I don't know, d prime, zj, zj star. This is the sum of the eigenvalues. So this is the trace of these things. And then you push the trace in, and then you cycle the trace. So each of those traces is 1. Like the trace of this is 1, since each of the CJs is unit norm by virtue of coming from the sphere. And then I sum up d prime of those. So I get this. So the first column of the eigensteps, someone in the eigensteps polytope has to have sum equal to 1. The second guy has to have sum equal to 2. The last guy has to have sum equal to n, etc. So that's where these are the equalities and inequalities that define the Eigensteps polytope, and it turns out that it surjects onto the polytope. This map does. So,
thank you very much.
You got it. Other questions? Okay. So I'll close with the third proof, which is kind of, I think it's pretty neat, pretty exciting stuff. The reason I say that is this was a project where I made it my own little excuse to learn the ideas in geometric invariant theory. I specifically roped in Tom Needham and Clayton Shonkwiler to explain to me and Soledad how this technology works, and I found it to be pretty enlightening. So I'll give you guys my own little dumbed down version of the theory. So first, I guess I'll motivate why this comes into play. Here we prove the following. So you look at the gradient flow ordinary differential equation. You initialize at some member of SDN, and then you flow opposite the gradient, in fact, the Riemannian gradient of this frame potential. Remember, the frame potential is a function defined on SDN. Okay, so this is a gradient flow that's swimming throughout SDN, this cross of spheres. Suppose we were to initialize at a frame that is full spark. What that means is every d by d submatrix has a non-vanishing determinant. These are points in general position. That's another way to say it. Then the thing you converge to will be a unit norm tight frame. Okay, so this is to say that a generic initialization gradient flow will send to a unit norm tight frame. This implies the Benedetto Fickus theorem intuitively, because if you have some critical point that's not a global minimum, it's going to have full spark frames in arbitrarily small neighborhoods of him, thanks to full spark frames being generic. And everybody, almost everybody in those neighborhoods are going to be sent to a global min somewhere else. So there is no basin of attraction, and therefore it's not a local minimum. There's no local model that that would explain that, unless it were not a local minimum. So the proof idea for this gradient flow result is it's asking for some sort of property, like an invariant. So we're looking for a property that is satisfied by full spark frames. It's preserved by gradient flow. It's also preserved by limits. And then finally, if you're a critical point that's not a minimum, then you do not satisfy this property. Okay, so the idea is if you start off full spark, you have property P, and then you do gradient flow, you keep having property P, you take the limit as time goes to infinity, you still have property P, and you know you're at a critical point because that's what gradient flow sends everybody to, but you know that that critical point can't be a non-minimizing critical point because that would imply not P. So you must be at a minimizing critical point, which is a unit norm tight frame. Okay, so I'm going to explain what P we pick, and we're going to motivate this using property 2. We want a property that is preserved under gradient flow and under limits. So right, so for 2, I'm going to first talk about what this Romanian gradient is. So the Euclidean gradient this is the gradient you would get if you forgot about the constraint that all of your vectors are unit norm. So this gradient is this guy. Okay. The Riemannian gradient is obtained by projecting the Euclidean gradient onto the tangent space to SDN at Z. So what you get is just that same matrix, but we're going to normalize the columns. Is that what I'm going to do? Let's say that's what I'm going to do. I'm a little suspicious about this description of the projection, but I'm going to let it go for now. What is true for sure is this thing is going to reside in the tangent space of Z, or the tangent space at Z of a certain manifold, namely GL of D cross the complex units, N of them. So this is a group. GL of D is acting on the left of Z, and then these scalars are acting on the right. We're multiplying each column of Z by its own invertible complex number. This creates an orbit of Z, and the Riemannian gradient is pointing in the tangent space to this orbit. So what that means is the gradient flow trajectory, it's going to stay in the orbit of your initial point. Okay, so I initialize somewhere, and all throughout my orbit, I'm staying, or all throughout my gradient flow trajectory, I'm staying in this particular group orbit of the initialization. Okay, so all this to say, there is some sort of symmetry calling the shots here, some sort of group action. And this is where geometric invariant theory becomes relevant. So geometric invariant theory, we're thinking of a reductive group acting linearly on a complex vector space. So we have some group that's acting on a vector space. So a natural thing when you have a group acting on a vector space or on any set is to consider the quotient. So the set of all orbits under the group action. The interesting bit is that in this setting, not all orbits are created equal. So in particular, we're going to give names to different types of points based on what their orbit smells like. So we'll say that some points are unstable. They're unstable if 0 is in the closure of the orbit. And then otherwise, we'll say it's semi-stable. Okay, so if for geometric invariant theory, these notions are important for coming up with a geometric notion of quotient. The idea is there are certain, like you have this family of polynomials that you want to use to separate these orbits, and the polynomials aren't going to be able to separate V from 0 if 0 is in the closure of this orbit. And so the unstable points are bad for this sort of detection. And so we have a notion of geometric orbit that just takes the semi-stable points and mods something out only with those guys. Okay, So for us, the thing that matters is we're going to have a property that is robust to gradient flow. It's also going to be robust to limits thanks to this closure kind of thing. And this proposition makes that clear. If you have a point that's semi-stable, then every point in the closure of the orbit is also semi-stable. Okay, this is a simple limiting argument. But the point is that gradient flow keeps you in the orbit. The limit keeps you in the closure. So if you started semi-stable, you end up semi-stable. More specifically, we're going to be taking our group to be GL of D. We're going to take V to be this space of tensors. So it's like we're tensoring up the columns of our short fat matrix. And we'll say that our short fat matrix has property P if this tensor is semi-stable. Okay, so it turns out that this is, in some sense, the correct choice of property for this. We satisfy property 2 thanks to this proposition, and then it remains to verify properties 1 and 3. For this, there's some really awesome technology from geometric invariant theory. It's called the Hilbert-Mumford criterion. What this says is you want to know whether a point is unstable or semi-stable. That amounts to detecting whether 0 is in the closure of this orbit. So instead of looking at the full group, you could look at a one-parameter subgroup, a subgroup that's parameterized by a single complex variable. And certainly, if 0 is in the closure of the orbit under that subgroup, that one-parameter subgroup, then you're unstable. And it turns out the converse also holds. If you're unstable, then you're going to be able to witness that with some one-parameter subgroup. And this is super useful for deciding whether certain types of points are unstable or semi-stable. So overall, we talked about 3 different proofs. One used Lagrange multipliers and Vertinger derivatives. Second used convexity and topology. And the last one used geometric invariant theory. I want to thank you for taking the time to listen to me. And at this point, I'll answer any questions you may have.